Catching the Light with the Rainbow Nation took place in September 2013 and was a large-scale, ambitious outreach event intended to increase the popularity and understanding of chemistry in Mafikeng and Durban, South Africa. The event was centred on a series of school workshops exploring chemistry, light and colour with rainbow as the central theme. This scientific outreach event involved a week of workshops in the University of KwaZulu-Natal in Durban for local high schools and a week of workshops in Mafikeng. Over the 2-week period, over 1,300 school children attended the workshops. There were also demonstration lectures for students and the general community, and there was the first ever Swansea University, Bangor University, University of KwaZulu-Natal Physical and Material Chemistry discussion group aimed at inspiring and developing strong international collaborations. This day involved over 40 presentations from postgraduate students of the 3 universities on physical chemistry topics. The aim of the event was to take chemistry, science and technology to a large number of children across a range of ages across South Africa and to spread our enjoyment, love and passion for science to as many as possible. The Catching the Light team consisted of a scientist from Bangor University in North Wales, 6 scientists from Specific in Swansea University, 4 scientists from the chemistry group Swansea University, and 5 scientists from the University of KwaZulu-Natal in South Africa.
Workshops are going to try to promote science and chemistry in the areas that we teach in South Africa, and they're all based on colour and colour chemistry and catching the light. So we do a lot of experiments, making solar technologies, making solar panels from fruit and using sunlight. So we use sunlight to make cyanotype prints, blueprints essentially, and things like this with the children.
We have lots of chromatography equipment, and this is not merely for research. It's also for our third-year students who get hands-on experience. So here you see the third-year students during their lab sessions doing the chromatography, and here as well.
Titanium dioxide is only photosensitive in the UV region of the spectrum.
We would require a transparent electrode on top, so the light can still reach the active layers.
Even further, one of the largest polluting is the textile industry.
And the memory chips themselves contain gold, a little bit of silver, and of course the borders will attract copper as well.
Spread out and coat the soil particles and lower the surface tension so that when water drops hit the soil, then it won't infiltrate.
In this 2 to 3 hour workshop, students made their very own dye-sensitized solar cells from everyday materials. The students were taught about the importance of solar and renewable energy, as well as how dyes can absorb visible light. Blackberries and blueberries were crushed and filtered to extract the juice and produce a natural dye. Glass electrodes with titanium dioxide films were dyed in the fruit juice. This allows the cells to convert visible light into electricity. Fruit teas were also tested as dyes.
Quick fingers. There we go.
A separate glass electrode was coated with carbon from a pencil to act as a catalyst. A conductive liquid electrolyte was injected between the 2 glass electrodes to complete the circuit. The solar cells were tested for performance outside, inside and under a bright lamp.
Right, that's more like it. Super. 400 millivolts. 300 kiliohms was.
The students were amazed at how easy it was to make a solar cell.
So first of all, did everybody enjoy?
Yes!
Does everybody love science now?
Yes!
That's good. Is everybody going to study chemistry? No. Okay, so if we knock the lights off, we want to do some photochemistry. We want to get some light into our reactions. What are we going to use? We need a light source. Our natural light source is the sun. This enormous nuclear reactor, 93 million miles away, generating an enormous amount of energy inside it, which makes its way to the surface of the sun. 5,500 degrees Celsius. The heat of the sun, that temperature, generates
light. If we look at the next slide, please, Mike. This is a demonstration lecture, but the safety officers said we couldn't do this one because this is a hydrogen bomb going off. And that's what reactions go on inside the core of the sun, and the energy makes its way out from the core to reach the surface. But if we did that, we'd take out the whole of Durban. Here's a little tungsten bulb powered by the battery. Now the thing about this tungsten bulb, and the thing about the spectrum that I showed you, is that the spectrum of the bulb depends upon the temperature of the filament. So if I take a filament and heat it up a little bit, we get a red light, this orangey red light. If I take the filament and heat it up some more, I get an orangey yellow light. If I take the filament and heat it up a bit more, I get a brighter orangey yellow light. If I heat the filament up enough, I'll get something approaching a white light. Now, the way that the spectrum, in other words, the range of colours and their intensity from a tungsten bulb vary with temperature, was the problem that was solved by the creation of quantum mechanics. Liquid light. We know that you can generate light from a chemical reaction because fireflies do it. Deep sea fish do it. They use light bioluminescence to send signals to each other. So I'm going to now try to make some liquid light. There we are. Reaction between luminol and hydrogen peroxide. So I like this reaction so much, I do it 3 times, but with a different dye. So there you go. Anybody seen Predator? It's an old film now, but that's Predator blood. And this one's for the milkshake freaks. So these chemical reactions are using up the energy in the reaction to generate light instead of heat. They absorb ultraviolet light, high energy light. They convert some of it into molecular motion. They start wiggling, start dancing around. That loses some of the energy. They give some of the energy to the solvent, perhaps. So when they're ready to emit the light, it's not UV anymore, it's visible. So we get the whole mixture of dyes generating lots of different colours as they dissolve. That's fluorescence.
I'm going to tell you why solar energy is the one that we really have to crack for the future of mankind. Okay? This is the sun. As Peter said earlier, it is an enormous nuclear reactor that's 93 million miles from the Earth. It gives us a lot of energy. Okay? The sun provides a massive amount of energy, and the sun itself is massive. To put it into context, if we weighed everything in our solar system, the sun would account for 99.8623% of our solar system. It is enormous. If we showed the Earth next to the sun, that would be the Earth, this small dot here. I'm not even sure if you can see it. You could fit the Earth over 1 million times within the sun. And it gives us so much energy that enough solar energy falls on this planet every day to power the planet for the next 27 years. The Dye-Sensitized solar cell is a dye, of course. So, what we have here is a piece of glass with some titanium dioxide on. It's almost transparent. This is one of the advantages of DSE, as we'll see in a bit. But we can make them aesthetically pleasing. So we control the dye that goes on this surface, we can control the colour, we can control the transparency by changing the particle size. So we can have opaque cells and transparent cells. What I'm going to use today, just to show how simple these cells are, is fruit tea from Pick and Pay. So this is just a natural dye. There's the kettle. So I'm going to put a few of these in. There you go, 6-7 tea bags. Here we have a dyed piece of TiO2. You see it's bright purple, that's the hibiscus dye. So that now is absorbing visible light, okay, and it'll work as a PV cell. At least I hope it'll work as a PV cell. There we go, the cable stopped it. So there you go, a solar cell made of So it's really simple, it's from everyday materials.
One of our workshops was based on cyanotype photography, also known as blueprints. This workshop was delivered in Mafikeng to about 200 students of age 12-15 over the course of 1 week. In cyanotype photography, iron 3 ions containing iron 3 citrate are reduced to iron 2 ions under light irradiation. These iron 2 ions react with ferricyanide to produce the blue ferric ferricyanide pigment called Prussian blue. First, the paper is sensitized in a solution of ammonium iron citrate and potassium ferricyanide and dried with a hairdryer. Then the kids had to choose from a selection of plants to image on their paper. The plant was laid flat on the paper underneath a piece of glass and then exposed to the sun. Alright, now, what follows is probably one of the funnest demonstrations of what you could do whilst waiting for your paper to get tinted. The print was finally rinsed in water to remove all of the ammonium iron citrate and potassium ferricyanide that did not react. This teaches the children how chemicals can react with light whilst getting them to produce lovely prints.
Taking the red cabbage you guys tore up, we've put some water in this beaker. We've put some water in the beaker. And now we're just going to boil it for about 15 minutes, okay? We'll come back to that at the end of the day, but we're going to make an indicator just like that. Now these 4 indicators, okay? Phenolphthalein, bromomethyl blue, Congo red and methyl red. They're the 4 indicators along the top. Don't worry about pH paper for now, we'll come to that. The next thing is we're going to test each of these different samples with the 4 different indicators, and you're going to write down the colour you see, okay? What colour is that?
Pinky.
The bicarb, the first one we did, sodium carbonate. That's base, yeah? Fill that out. There you go. Yes, sir. So that proves it. Neutral, acid, base. Here's your red cabbage as an indicator.
Another pretty things we use are these things. Have you ever seen these? This is a glow stick. So what this is in the middle there's a little glass vial of a chemical called hydrogen peroxide, and on the outside is a dye. And when you break it, the two chemicals react, and when they react, they make light. Okay? So if we break it, make lots of light. We can change the dye and make red light. We can also change the dye and make blue light.
Wow, the blue one is bright.
Yeah, the blue one is bright, eh?
This is very nice. One color for each finger. That's what we want. So what happens then when you have all these paints on your hands? So you take the torches to show you the beautiful drawings you've been making. Look at this. Isn't this so pretty?
Nice.
This is very nice, huh?
Wow.
Look at your arm. Very nice.
Watch.
Oh. This is very pretty, yeah?
The needs and the requirements of today, while not compromising the needs of tomorrow and future generations. So you should have a think about what that means. Okay? Really, what do we need? We need shelter, food, what else? Yep. Oxygen. Water, exactly. Okay? Now, at the moment, those things where there's a lot of things we do that pollute. So that means we're polluting the air, we're polluting the water, all the fuels we're using to stay warm, we're burning those up. So everything we do helps us to become more sustainable. Cal works with water treatment, so he's trying to come up with a way of keeping our water clean. When we have dirty water, cleaning it. I'm into recycling. So everything we're using up, all those resources we need, and not doing anything with, well, I try and figure out ways that we can get them back and use them again and again and again and again. These guys, they're into solar energy. So they try and come up with energy for us, so we don't have to burn fossil fuels and pollute the air. And we can use those valuable resources for other things. And that's what more sustainable means. Using new technologies, we can have everything we need to live today without compromising the needs of our children. And you guys are the next generation, and your children, and your children.
Positive earth energy, positive heat. Okay?
Right.
High five!
For some of you once again, but it's just like to welcome you here this evening. As you know, we've just spent a week with Swansea Bangor science tour, science group, and our eyes have been incredibly opened by what's been going on. So maybe just to start off by firstly saying thank you so much to the group for coming out. I was saying earlier to some of you that you probably won't see the difference you've made because you'll be in Wales and we'll be wishing we were in Wales. But I have no doubt that almost 1,000 kids that you have actually exposed to science in South Africa and in Durban and now in Mafikeng have had a wonderful time, and that exposure is going to see them not only doing well in science but maybe taking it a lot further. I'd also like to thank, especially like to thank Matthew, who has led the team. Much of this was his planning and his idea, and then obviously a wonderful team. You know, when you look at them, when I looked at them in the beginning, I kind of really didn't believe that they were actually scientists. You know, the one had lots of hair. One had long hair, other had no hair. But of course, we know why Bruce is. Where's Bruce? We know why Bruce has got no hair because he raised £800 for SOS charity by cutting his dreadlocks off just a couple of weeks ago. So much appreciated. And I think you've discovered SOS Africa this week, you Welsh and Canadian and French and this group, and you discovered that we're a family here. Around this table are folk that have hosted you, and I really appreciate that, guys. This has really been a wonderful week, and it's actually sad to see you guys go because not only have you come as scientists, but you've come and become part of our SOS family. We know that you're going to go back. Matthew's going to go back with a whole new wardrobe. But we are a family here, and we're going to miss you. And we really hope you're going to come back out here again in the next couple of years. And hopefully then you'll make it up to Cape Town as well, and make it a really worthwhile South African trip the next time.
To them, I really want to thank SOS Africa for the opportunity in conjunction with Mr. Matthews and Ms. Spinard. You all know Ms. Spinard from the preparatory school. Yes. She was the teacher of some of you. That give us this opportunity to host the scientists here at Goreview. Really, it was an honor for us. For me, as the principal of the school, what really caught me and it inspired me again is your passion commitment. And I realized that teaching is not only a job, it's a call, and if you don't have the passion, we cannot develop the stars. And I'm really fortunate to say that I'm working with an excellent team of educators here, and obviously the stars.
And hopefully, one day we'll be back to do it again. Thank you very much.
As well as the workshops, schools, sports and science equipment were donated to the high schools involved, as well as the Early Learning Centre and the charity SOS Africa.
If you're happy and you know